I'm going to present some work that's been done by Yuzhan Wang, who finished her PhD here a few years ago. And this is basically the third paper from her thesis that's in revision now for economic geology and is going to be resubmitted imminently. These are our sponsors, mostly NSERC and Valley. Just a bit of background. So as I mentioned, there are three papers. This is the third. The original problem is why the mineralization in the so-called sublayer, the inclusion-rich unit at the base of the subarachnoid complex, is selectively associated with ultramafic inclusions. And this extends to what's called inclusion quartz diorite, an equivalent phase that's in some of the offset dikes, and even the footwall breccia, which is an anatectic breccia at the bottom of the sequence. And so the approach has been, at least for this part of the study, to integrate all the textural, geochemical, and petrological data that she gathered during the first parts of her thesis with the many geological constraints. And we've got new constraints then on the timing and mechanisms of the formation of these units. And we're hoping to add to this with current work by Dustin and Sandra and Henning Seibel that will do additional isotopic work to test some of the conclusions that we reached here. These were some of the problems, the thermal and convective history of the impact melt, the relationships, as I said, between the ultramafic inclusions and the mineralization, the genesis of the sulfides, there's a couple different models for that, localization of sulfides, also a couple models, and the relative timings of the offset dike margins and cores. We know well, I guess we know the relative timing of those, but the timing relative to the impact history, and the same with sublayer norite and the anatectic footwall breccia. So these are the papers. If you're interested, they'll be in the version that's posted. I don't need to tell many of you about Sudbury, where it is. I'll be talking about, if you're not familiar with Sudbury, about offset dikes, which are these red things. There's radial ones and concentric ones. And sublayer, which is this purple unit that is located right along the bottom, selectively in depressions at the bottom, which can be in embayments or funnels or troughs. This is a stratigraphic section showing the stratigraphy. I'm not going to talk much about any of this. Contact sublayers down here. There's a footwall breccia unit that is associated, underlies sublayer in most places. And then these are some of the dikes represented here. This is a surface section of the whistle funnel that Henning's working on right now. I just want to point out that this is basically the main mass. There's some mafic norite here, and then a bit of sublayer down here, and then mineralized sublayer, and then the sublayer is this unit down in here. And this has been modified. This was mapped by Ed a long time ago, but it's been modified now, and a lot of this has been mined out. But this just shows the sort of stratigraphic relationship between them. This is what sublayer looks like. You can see lots of spotted sulfides. These are some ultramafic inclusions. There's lots of other types of inclusions, mafic. There's even inclusions of quartz diorite and things like that in inclusion quartz diorite. This is less mineralized sublayer. You can see just some specks of sulfides here. No ultramafic inclusions, but plenty of gabbroic and mafic inclusions. This is what one of the dikes looks like. It's got a margin of quartz diorite, which is very fine grained with often a radiating pyroxene texture. And then this is the inclusion rich, and in this case, sulfide rich internal core. And this is what footwall breccia looks like on the North Range. It's very leucocratic because you're basically melting Levack gneisses. You can see fragments of the gneisses in it. And on the South Range, in this particular location, the greenstones have been melted and mobilized up through the lower part of the Sudbury igneous complex. So I'm not going to dwell on this, but this study that Yuzhan did backed up the previous ideas that there were basically three types of xenoliths, antiliths derived from an early contact phase of the subarachnoid complex, the main mass, and then both local and exotic xenoliths. And it's the exotic xenoliths that are the most interesting and the ones that appear to be most selectively associated with mineralization. There's some features in here. I'm not going to talk about those, but they'll be in the presentation. One thing we needed to do was investigate some of the early thoughts regarding how superheated the SIC was. Impact models predict that. The empirical observations suggest that based on looking at other examples of large impacts. In the distal apophyses of some of the quartz diorite dikes, there's an example from Trill. The quartz diorite is totally aphanitic and sometimes has spherulitic textures. And the inclusions in marginal QD, which aren't shown here, but we're shown in the other slide on that, are very sparse to begin with. And if they are, they're locally derived contact rocks. And so that's a constraint then that at that point there was no debris in the impact melt. And there have been exotic zircons found in the Onping Formation, and none reported in quartz diorite, indicating that they were melted or reset. So in terms of the relationship between the inclusions and mineralization, and again, I'm covering a lot of material here and leaving a lot of things out, so this is just a high-level overview. There's some genetic relationship. Only the antiliths contain sulfides, but the others may have been preferentially disaggregated. So that's a possibility. Hydraulic equivalence seems reasonable. The sulfide droplets are usually smaller than most of the inclusions, but some of the inclusions are very large, so that's an imperfect relationship. But the clearest reason is just survivability. As we'll see in a second, ultramafic inclusions melt at high temperature, but not at low temperature, and molten sulfides are miscible at the lower temperatures. And so that explains their association. They're also both fairly dense. Let's see, I don't know why that went so slow. We also have evidence for a rapid cooling event. There are no exotic ultramafic inclusions in marginal QD, but yet we do have them in IQD, and that means that the temperature was hot here and cool here, and that it happened fairly quickly, as I'll explain why in a second. And the exotic ultramafic inclusions don't really, very often, it's pretty rare, just in one category, exhibit any evidence of partial melting. So, but they're still rounded, and so they may have been dissolved, and there's a difference between melting and dissolution that I can explain later if someone's interested. But we must have maintained superheat, and that's because the exotic ultramafic inclusions must have been acquired after emplacement of marginal QD, and that requires additional thermomechanical erosion. We have lots of locally derived inclusions that requires thermomechanical erosion. So there's a long list of things in here that indicate that we still must have had systematically large amounts of, or at least small amounts of superheat. It doesn't take much superheat to keep the magma convecting. These are some melting rates of wall rocks. I think what I missed there, I missed the melting rates on the inclusions when the slide was slow to come up. And you can see the ultramafic inclusions here basically stop melting after you get above about 1300. All these inclusions melt at more or less the same order of magnitude, depending on their size, at the higher temperatures. And so this explains the survivability of the ultramafic inclusions compared to the others over here. Now, the melting rates of the wall rock, that's actually slower because in an inclusion, you're melting all sides of the inclusion, but the underlying footwall rocks, in fact, you're just melting the surface of them, or if it's debris, then we're treating them like inclusions. And you can see the ultramafic rocks that were in the footwall in some locations were melted much more slowly. These are the erosion rates here, meter per day, 0.1 meter per day. And that the metasedimentary rocks, of course, as one would expect, would melt at much lower temperatures or more rapidly. So the thermal history then, as we see it, is that it was superheated for a stage about 500 degrees above the liquidus during impact, compression, and excavation. It was rapidly cooled to about 1300, so somewhere above the liquidus of 1200 between the emplacement of marginal and QD. And a constraint on that is that it takes about 1 to 5 days using conductive cooling calculations for the marginal phase of the of the dikes to have crystallized before we intrude then the interior phase. And then it cools quickly to about 1200 and beyond. Origin of sulfides, there's two end-member models. I don't have time to talk about this, but one is X solution. That's sort of the model most people, Peter Lightfoot and Reed Keyes, prefer. And then another one is that with increasing evidence now that volatile elements have been lost from the impact melt sheet, and the thionoping in particular, is that the isotopic data then support a model where we've lost a lot of the sulfur and reacquired it during later post-impact thermomechanical erosion. In terms of localization of sulfides, there's two models for this. One sort of settling and convective sweeping as the sulfides exsolve from the impact melt. The other is that they're generated more or less in situ by thermomechanical erosion. These are not mutually exclusive. There have been experiments done on how things settle in convecting magmas, and this is an experiment that was scaled very similar to Sudbury, actually, that shows vigorous convection at a Rayleigh number of only 10 to the 8th, whereas Sudbury, because it's much thicker, is estimated to be 10 to the 14th. And the important thing is that there's no convective sweeping along the bottom of any significance, and you do get settling of particles at the bottom, regardless of the convective velocity. And that was shown in a very nice paper, classic paper by Martin and Noakes. These are the settling velocities of things. Again, I think these are all as you'd expected. Things settle faster at lower viscosities and higher temperatures, and they settle more slowly at the lower temperatures and higher viscosities. And the different phases, xenoliths, ultramafic xenoliths here in green, and felsic xenoliths, and then the sulfide droplets here are smaller. But you can see there's a bit of an overlap and a lot of flexibility here in deciding how fast you want things to settle. And then this is residence times on the right. In terms of the option to that, another is gravity flow of the sulfide. So they collect on the contact here, which is greatly exaggerated. They generate basically a debris flow like in sediments, flow down the contact and get trapped in the abatements. This often produces something called run out, where this thing actually accelerates down and pulls everything with it and leaves a barren contact as observed. Another thing that happens in certain cases, and this might apply on the North Range where there's a lot of topographic relief, is that there are, as the sulfides move, they move over what are called hydraulic jumps. And you can actually preferentially collect sulfides in those fluid dynamic situations. This is just a table to show you some numbers that I'm going to talk about later. So that's for your information for later. But this is sort of scaling what might have happened at Sudbury with what happens in normal debris flows, and the relative density. So the density of the proto-sublayer, inclusion, sulfides, plus impact melt, relative to the impact melt, vary with the amount of sulfide, impact melt, inclusion. They get higher, obviously, with sulfides, and they're basically in the range of 1 to 1.7 as we calculate, and less than the range for sedimentary debris flow. So they're actually, the relative density is less than a sedimentary debris flow, and we know they flow. And then the relative viscosity is harder to calculate because there's a discontinuity here between where impact melt and versus sulfide is the continuous phase around things. But low-grade proto-sublayer with less sulfide is about 1 to 10, which is less than the range for sedimentary debris flows. And inclusion massive sulfide goes up to about 830, which is less to more than the range for sedimentary debris flows. So we think they'll flow like debris flows, and Yujan's in the process of finalizing some of the calculations on that. This is our inferred timing. It's a big table, so I've made some cartoons at the end, but we've got different timing stages across here. Cratering process, what happens here, what gets produced, collapsed debris, local xenoliths, ultramafic xenoliths, what gets melted and eroded, offset dikes, when each phase is in place, when the sulfide forms, when it then crystallizes, and so forth. So I'll just show you a couple cartoons here. This one's a little more detailed. Here's contact and compression up here with time across here and very rough temperature. These processes don't really coincide to time versus temperature extremely well. And this is modified from Peter's book. But contact and compression, we produce all these things in here. There's isostatic rebound. I'll show you what that looks like in a second. And then a collapse process of the peak ring and crater walls. And we think that's when it generates inclusion quartz diorite. And then finally, as things sort of cool down a bit, we're still eroding, we form sublayer norite and footwall breccia. And then we crystallize basically the main mass. So here's a cartoon, oops. And so the bolide, which is thought to actually be a comet these days by Joe Petrus and Baltz Camber, but could have been an asteroid, contacted the planetary surface. It was compression, generation of the impact melt. And this was the only time when the impact melt was inclusion free. So that's when we think we generated the quartz diorite, the marginal quartz diorite part of the dikes. Immediately following that, and this is like seconds, just a few seconds, the whole cavity is gravitationally unstable and it rebounds and forms a large peak. The larger the impact, the larger the peak, and then that just as quickly falls down and collapses, and that process is going to generate a lot of impact debris. And we think that then is what cooled the impact melt and allowed the quartz diorite to intrude. A lot of this collapse is going to be dilational. We then deposit the Onaping Formation. We have no idea what that did, but it came down with not a thump, but a pretty good, pretty rapid accumulation, and may have squirted things around a little bit. And then at that stage, we start to finalize the formation of sublayer and start making footwall breccia around the funnels and in embayments. So that's the story. I don't know if there are any questions.